Okay, so I hope everybody is doing well. Today we are going to be looking at the final couple problems of our section 2.4, which is the mechanical properties of materials. So on Thursday during class, we went through kind of our introduction to our mechanical properties. We defined we drew stress strain diagram, and we defined some of the important points along those stress strain diagrams. We talked about Hooke's law, where we can remember that stress is equal to modulus of elasticity times strain, and then the same thing goes for shear stress, but it is with the modulus of rigidity times gamma. Let me make this pen a little bit thinner. Okay, there we go. So we defined Hooke's law. Poisson's ratio we defined with the Greek letter nu. It was the negative ratio of the lateral strain to the longitudinal strain. And then finally we got to our material property relationship, where we said that the modulus of rigidity G is equal to the modulus of elasticity E divided by 2 times 1 plus nu. Okay, so those were kind of the 3, or I guess 4 equations that we're really worried about when we're talking about mechanical properties. So we went through that, and then we started working on some examples. So the purpose of today's video is to just complete the last 2 examples that we did not get to in class, which we will do right here. So in this particular example, what we've got is 2 rubber blocks that are sandwiched between 3 rigid plates of, I'm assuming, steel or some type of metal. And the blocks are bonded to these plates, and then the plates are being supported by whatever this is on the left and the right. Okay, so if the plates are rigid and the shear modulus of the rubber is G, right? We know G. We hypothetically know G. We are asked to determine the displacement of the plate, this delta, determine the displacement of the plate at A under the vertical load P. And we're also given to assume that small angle rules, which, you know, sine of a small number is a small number, so sine theta is equal to theta. And then also with tangent, it's tangent theta is equal to theta. Okay, so let's just start off with our free body diagram. So I just want to ask a conceptual problem first. Let's change this to red. All right, if I've got P acting right here in the middle, acting straight down, and it's all supported and it's in equilibrium, does it make sense that we're not going to have a P over 2 reaction at each end of the sandwich plates? That should be instinctive to know, to be able to see that, but sometimes it's not. So, but if we can come down here and we'll draw our free body diagrams, okay? So step 1, draw a free body diagram. And the easiest way to do this is to draw a free body diagram of a rubber block, either the left one or the right one. Okay, so I'm just going to stick with the one on the right. So in its original position, the rubber block was rectangular, but then in its deflected position, it gets moved down because the load deforms, the block. Now, you'll notice that the forces that I drew on the rubber block are P over 2 and P over 2 and not P. When we're looking at the rubber block, this P gets applied to the metal plate, right? Well, this metal plate gets supported by each of the blocks. So, acting along this plane right here is P over 2, and acting along this plane right here is P over 2. So each of these rubber blocks takes a couple force of P over 2. All right. So we know the width of this block is A. We know the height of this block is H, and we know the in and out dimension of the block is B, but that is in and out of the page. Okay. This dimension here is defined as delta, and this dimension, or this angle right here, that will become gamma, right? We've got a material is being displaced, right? Remember all the problems that we did when we were looking at shear strain. Shear strain is defined as the change in angle between two lines that were originally perpendicular to each other. So the line A and the line H, they were originally perpendicular to each other. You know, this was originally a 90-degree angle right here. But now, after load, it is deformed, and we have some new angle that's developed, and we'll call that gamma. All right. But we also know that, looking at our diagram here, we can say that tangent of gamma is equal to delta over A. But we also know that tangent of gamma just is going to be tangent because of our small angle rules. So delta over A then just equals gamma. All right. And the problem is asking us, what is delta in terms of our known variables? Our known variables are P, A, H, B, and I think that's it. And G. Sorry, we also know G. So we're trying to find delta in terms of P, A, B, H, and G. All right. So we found the shear strain that's acting on our free body diagram, gamma. We've already defined it as delta over A. What about the stress that is on this block? You know, we've got to relate G here somehow. We don't know an E, and we don't know any kind of normal stress. So my mind is thinking that we need to work with something. We need to figure out an equation where we're working with stress and strain and G, which is, we're working towards Hooke's law here. So we're looking towards stress is equal to G times gamma, and we just found gamma to be equal to delta over A. G is a known, and we just need to figure out what tau is now for the shear stress. What is the shear stress that acts on this rubber block? And so that'll be step 2. And let's say that step 2 is stress on block. So again, shear stress, we've defined it many times already, is just V, if I can draw, V over A. But the question is, what is the shear stress on this block of rubber? And we just got to identify what V and A are for this particular problem. So it may be evident to some, it may not be, but V is going to be the amount of load that shears this block, and it's going to be P over 2. So P over 2 is the V. And the area over which that P over 2 force acts is going to be the area of the rubber block. But it's not going to be the area AH. It's going to be the area HB, if that makes sense. We got to look at this in kind of a 3-dimension sense. So this P over 2 force acts over an area of BH. All right. So let's just put that together then. Let's just condense that equation down, and that becomes P over 2BH. So at this point, we have everything we need to know, and we just apply Hooke's law. We know our strain and we know our stress, so we can apply Hooke's law and solve for our variables that we're looking for. So step 3, apply Hooke's law. And what we get is that tau is equal to G gamma. Tau equals P over 2BH times G, and then gamma we found out was delta over A. And if we have this equation, we've got an equation in terms of delta, in terms of all of our other known variables, P, B, H, G, and A. So just rearrange this equation then, and we get that delta is equal to PA over 2G, B, and H. And that is our answer. That's what we're looking for. All right. So in this scenario here, if we had this particular problem, if we actually knew what force was being applied and we knew the physical dimensions of our rubber block and our plates and everything, we could calculate how much this is a shear spring, how much that shear spring would deflect. And it would be PA over 2GBH. Okay, so that concludes that example. And now we're going to move on to our next example, which is on page 40. So we've got an aluminum bolt, diameter of 8 millimeters, and it fits through a magnesium sleeve up here, magnesium sleeve that has an inner diameter of 12 millimeters and an outer diameter of 20 millimeters. So it's got a wall thickness of 8 millimeters. The problem is asking us to determine the strain in the sleeve and the bolt if the bolt is tightened up to a point to where there's 8 kilonewtons of tension in the bolt. So does that make sense to everybody? If this nut here was not tightened on the bolt at all, there would be no tension in the bolt, right? But as we tighten this nut down on the bolt, it's going to try and stretch this section of the bolt in between the head of the bolt and the nut. It's going to stretch it, and by doing so, we're going to induce tension in this bolt. All right. If we can crank on the bolt enough to where we get 8 kilonewtons worth of tension in the bolt, what is going to be the strain in the bolt and what is the strain in the sleeve? All right. Second part of the problem is, what is the diameter of the bolt after it has been tensioned? Assume material A is rigid. All right. There is no deformation that happens at material A. And then we're given modulus elasticity of aluminum to be 70 gigapascals, modulus elasticity of magnesium to be 45 gigapascals, and then finally the shear modulus of aluminum is 26 gigapascals. All right. So again, we kind of think about what have we been given, what are we looking for. We've been given a force and an area for the bolt. So right off the bat, we can find the stress in the bolt. So I'm going to say that is step 1, stress in bolt. So sigma in bolt, it's just P over A, where P, we've got 8 kilonewtons of tension in the bolt, so P is equal to 8 kilonewtons. And then the area is pi over 4 times d squared, and that's 8 millimeters, right? So 8 millimeters squared. And if we run those numbers out, what we get is 159.15 megapascals. All right. And if we draw a free body diagram of our bolt and sleeve, if the bolt has 8 kilonewtons of tension, let's draw the free body diagram of the bolt. Okay, I'm a terrible drawer. So here is a free body diagram of the bolt, and it has 8 kilonewtons. 8 kilonewtons of tension in it. For this free body diagram to be in equilibrium, the forces that act back up on the bottom of the bolt head have to be 8 kilonewtons as well. But since it's not going to be two forces, right? It's that these forces act in a ring all around this here. I'm going to just denote this as the sum of these forces has got to be 8 kilonewtons as well. And if we were to then draw the free body diagram of the sleeve, we would see that there has to be 8 kilonewtons, a total of 8 kilonewtons acting on the cross-sectional area of the sleeve, right? Which is, is a pipe shape, right? It's not a solid rod, it is hollow. So if we've still got 8 kilonewtons, and at this point the sleeve becomes in compression, so we've got 8 kilonewtons of compression in the sleeve acting on the cross-sectional area of the sleeve. So then we can say that step 2, we can find the stress in the sleeve. And guys, I'm going to go ahead and go back up here to our stress in our bolt equation. I'm going to rename that stress in bolt. We'll call it stress in the aluminum bolt, just to make all of our subscripts cohesive. All right, and then so for the stress in the sleeve, I will call it sigma mag for magnesium. And it's still just P over A. P still 8 kilonewtons. That's still the load that has to be transferred through the sleeve. But now our area of that sleeve is pi over 4, but it's not just 20 millimeters squared, and it's not just 12 millimeters squared, and it's not even 12 minus or 20 minus 12 squared. It is 20 squared minus 12 squared. Okay, guys, don't confuse that. This is not the same thing as this, right? This is wrong. All right, so it's d squared minus d squared. And if we run through this, what we get is 39.79 megapascals. All right. So at this point, we have what we need for the first part of the question, is determine the strain and the sleeve. The strain in the sleeve and the strain in the bolt, because we now have the stress in the bolt and the stress in the sleeve, and we know E of the bolt and E of the sleeve. So just apply Hooke's law to get the strains in each of the bolt and sleeve. So step 3, we'll just label it, strains, whatever. So we know that sigma equals E epsilon. So the strain then is going to be equal to sigma over E. So I'm just going to say sigma strain aluminum, epsilon aluminum, is equal to sigma aluminum over E aluminum. And what we get is 159.15 megapascals divided by E aluminum, which was 70 gigapascals. Make sure you're working your units correctly. And when we run through that number, we get 2.27 times 10 to the negative 3. That is the strain in the aluminum. And we will repeat Hooke's law for the magnesium sleeve. So epsilon mag is equal to sigma mag over E mag, which is 39.79 megapascals divided by E mag, which was 45 gigapascals. And when you run that out, again, pay attention to your units. What we get is 8.84 times 10 to the negative 4. All right, so that is the answer to the first part of the question where it wanted to know the strain in the sleeve and the bolt. The second part of the question, however, it wanted to know what is the diameter of the bolt after it has been tensioned, right? After it has this 8 kilonewton load in it, it's going to stretch it a little bit, and we know that if we stretch that bolt a little bit, it's also going to get just a little bit thinner, right? So we need to figure out then, if I'm asking you for a lateral deformation, y'all's mind should immediately start to think about Poisson's ratio. So for the bolt, which is the aluminum subscripts, we know our longitudinal strain, E or epsilon aluminum, because this is the strain that is in the longitudinal axis of the bolt. What we want to know is the strain in the lateral direction so that we can calculate the new diameter of the bolt. But we will need Poisson's ratio to find that. I mean, we're not given Poisson's ratio, but we can use our material property relationships to figure out what Poisson's ratio is for aluminum, because we know E and G. So let's step 4 here. Relationship. We know that G is equal to E over 2 times 1 plus nu. G, we said, was 26 gigapascals. Is that right? 26 gigapascals. E is 70 gigapascals over 2 times 1 plus nu. Just solve this equation right here, and what we find out that nu for the aluminum comes out to be 0.346. And again, that value appears to be correct, right? Because it is between 0 and 0.5. Poisson's ratio will always be between 0 and 0.5. All right? So now that we know that, we can take our longitudinal strain, which is this 2.27 times 10 to the negative 3rd, apply Poisson's ratio, and we can find a lateral strain. So if we know that nu is equal to negative strain lat over strain long, nu equals 0.346. We're trying to find strain lat, and we know strain long is 2.27 times 10 to the negative 3. Solve that equation, and we find that strain lateral is equal to negative 7.86 times 10 to the negative 4. Now again, I know in class we said don't worry about that negative sign, but what all this denotes is that a negative sign means that the dimension is going to get smaller, and a positive number means that the dimension will get bigger, right? So if our lateral strain is negative, that means our new diameter of this particular bolt is going to be smaller than the original diameter, which makes sense, right? Because it's in tension, it's going to stretch longitudinally, so it should contract in the lateral dimension. So if we take our strain then, and I've run out of room, let me how do I want to, can I just do this here? Make a new page here. You guys may just have to like write on the back of the page. All right. So if I know our lateral strain is negative 0.786 times 10 to the negative 4th, and I know the original diameter, we know that strain is delta, for this particular equation that we're working with, is going to be delta D over DO. We know the strain and we know DO, so we can say that delta D is equal to strain DO, which is negative 7.86 times 10 to the negative 4. That's the strain, and the original DO was 8 millimeters. So our delta D then comes out to be negative 6.29 times 10 to the negative 3rd millimeters, which means that our final diameter, our diameter of the bolt after it has been tensioned, we'll call it DF or D final, is just equal to DO minus delta D, which is just going to be 8 millimeters minus our delta D. So this is where I'm trying to tell you guys, don't worry about these negative signs. That you don't let yourself get tripped up by these negative signs, because if you just plug this into this equation, your final diameter is going to be bigger than your DO, and that's not correct, right? So our delta final, then we're going to take 8 millimeters minus this delta D in millimeters, and what we find is that our final diameter is 7.9937 millimeters. Okay. So that is our last example on our section 2.4. If you guys have any questions about these notes, please email me or get in contact with me somehow. I'll see if I can't work these videos out. If you are struggling with this, there are plenty of YouTube videos out there that you could go out there and watch over material property relationships. But this should be a wrap on section 2.4. So our next section, I believe, we are going to start talking about axial members, where we're talking about axial stress. Now, we've already introduced quite a bit of information on axial members, but what we're going to do next is we're going to start looking at the deflections of axial members, what the equations are, as well as looking at thermal effects, what temperature changes in materials, how it affects the stresses and strains inside members as well. So that will be our next section. We'll be starting chapter 3 shortly, which will be all about axial members. All right, that concludes this video. Have a good day.